Good. So, welcome back after a long gap. So, what I'm going to do is, I'll assume that, like me, many of you have forgotten many things, including notations. And so, in order to make the rest of the course reasonably accessible, I think I'll just quickly review a couple of facts which will be helpful to us. Remember that in this course, up to now, we've been discussing a model called the MSSM, Minimal Supersymmetric Standard Model, plus some supersymmetry breaking terms which are explicit and soft. And all the consequences that we have derived from this model, including mixings, which will be the subject again of today's talk, follow from the potential, which comes from two sources. There's a potential coming from the superpotential of the MSSM. From this, we have to take W prime and take the mod square. And then there's a potential which is explicitly added by hand as the soft SUSY breaking terms. So the sum of these two is responsible for all effects of the standard model at tree level. And this superpotential, to remind you, this will also remind you what are the fields we're working with. It's very simple. There's a coupling between the two Higgs superfields. And then there is this kind of thing, repeated 3 times. These terms that are repeated 3 times are for, this is for in the electron sector, and it involves the right-handed electron, which of course as a superfield occurs in a chiral superfield E bar, which really contains the left-handed positron. And there isn't a corresponding term involving the neutrino because we are working in the approximation when neutrinos are massless. And there's a separate term which gives a mass to the down type quarks and squarks, and one for the up type. Okay, the index small I and j goes from 1 to 3, and that runs over generations. So in such a term, what appears really, as far as the fermions are concerned, will be the down quark as well as the strange quark and the bottom quark. In this term, we'll have the up quark, the charmed quark, and the top quark. And in this term, we'll have the electron, the muon, and the tau electron. And we won't have any term involving the 3 neutrinos under our assumptions. And this is enough of a superpotential for all purposes. These will generate Yukawa couplings for fermions, as well as they'll generate potential for the scalar partners, the fermions. And all other terms that we could think of writing down are forbidden by discrete R symmetry, which we already discussed. Okay. So as far as the MSSM superpotential, that's straightforward. Then to this we should add the terms coming from soft SUSY breaking, and those are terms of the form okay. So here what happens is we get terms which give masses to the fermions. So from L soft we have a whole bunch of terms which I'll classify as follows. Try to follow this notation. So we have L I L star M L square L I L J L tilde. So what's this? This is a doublet. That's why it's called L. In fact, it's just the scalar part of this doublet, which is called capital L. So these are left-handed lepton doublets. So they include electrons and neutrinos, and then their copies in all generations. But because of the tilde, these are the super partners. So these are all scalars. So these are fermions, electrons, neutrinos. And we have a generic mass square term which mixes all generations. That's allowed. And that will take care of the left fermions. which are the superpartners of the left fermions, the left leptons, which are superpartners of the left leptons. But then there are right leptons, namely right-handed electrons, and correspondingly they have superpartners, which are again scalar, but which are called electron EIR, and the tilde says that it's a selectron, and so there can be a separate matrix for that. Okay, and that takes care of all the leptons, or all the leptons, and you repeat the same exercise for all the quarks. It's pretty easy to guess what's going to happen. In place of this, you will have the squat, left-handed squawk doublet, and in place of this, you will have right-handed squawk singlets, one for U and one for D. Okay, I'm just repeating this because I think people need to get in the habit of thinking out how we think about all the superpartners, and they are classified just according to the quantum numbers of the original fermions. So it's not very difficult. So the terms are Q tilde I left star, then there is a mass matrix for that. Q tilde J left. This is just a copy of the thing for electrons. And then there's up. This is new in a sense because the up particle in the electron sector is the neutrino, and we didn't put any mass for that. But here there is one. So this has its own m square. And finally, the same thing with up, UIR into DI. So these are the mass terms, but that isn't the end of L soft. By the way, people remember all this, I don't need to go into it again. Is it helpful that I do it once more? Okay. Besides this, we are in principle allowed a term in L soft which has not phi star structure but phi structure. Okay, where phi is the complex scalar inside one of these superfields. The problem though is if you look at these superfields Q, L, E bar, D bar and U bar, you won't find any of them, any pair of them in fact, which have the right quantum numbers to be written in the form of a phi I, phi j term. Okay, because the phi I, phi j term, whatever it is, has to be neutral. The only pair that you can allow is actually a phi from H1 and a phi from H2. These two you can, these two make, in fact you can see it from this Lagrangian because the only bilinear in this is H1 dot H2, and if there was any other bilinear we could think of, we'd have written it. Okay, so that means that we have a term minus, or we have a term that we parameterize as P mu H1 dot H2 plus complex conjugate. So the logic here is that from here we'll get a term small h1 dot small h2 with coefficient mu, actually mu square in the ordinary potential, and then we correct it by a term small h1 dot small h2 with a coefficient p mu where b is arbitrary. Okay, and then there's a term, there are cubic terms which are very important, and they take this form. H1 dot L tilde IL, and then these FE, which are the generation mixing matrices occurring there, but now we correct them by multiplying by an arbitrary matrix AE. So this is just our way of parameterizing this arbitrary matrix. So that's one cubic term. Another cubic term this, written in the same spirit, FD, AD, okay. And then finally, Q tilde L H2, FU. So again, it follows the same sort of pattern. Whatever we do for up and down quarks, we also do for leptons, but we don't do it for neutrinos. I'm now not sure why we don't do this for neutrinos. Somehow we don't.
So we just never write that in neutrinos.
We don't have right-handed neutrinos, why we don't. Thank you. correct. Is this correct? Stop. Since we don't have a right-handed neutrino, we don't have a right-handed neutrino. But of course, in real life, we actually have both. So there has to be some sort of correction to all of these things incorporating neutrino masses. But as I said, I postponed all that. It's just the scale of those masses makes it possible to consistently do all this without them. So this more or less is the end. Then the last thing in the soft Lagrangian is the gaugino mass terms, which since I don't need to focus on them now, I'm not going to write them again. So these are bare mass terms for gauginos. So that completes my lightning review of the potential of the entire MSSM plus soft sector. And we've been exploring consequences of this. And last time what we did was to notice that from this potential, you find that there is generically mixing among the fermions. And it's quite a lot of mixing. It's really a mixing between 6 objects, as I'll explain now, and the 6 at a time. And the 6 objects are, for example, the 3 selectrons in 3 generations with the left index, which means they're partners of the left electron, and the 3 selectrons with the right index. Okay, all 6 of these actually can mix. With fermions, obviously, you cannot have left and right fermions mixing because that violates Lorentz invariance. But their scalar partners are just scalars, so they can perfectly well mix. And the point is that they mix very generically in this theory. And that's a huge amount of mixing. It makes for very complicated notation, as well as it makes for interesting results. Last time I actually did write down everything that's needed to study this mixing, and I won't repeat it in exactly that form. But instead, I'll just summarize it in some nice matrix notation, and then we'll try to explore the consequences. So the topic today is again fermion mixing, and we'll see a few nice physical facts emerging from this discussion finally. I also hope to conclude this discussion today, and from next time I want to talk about the Higgs sector of the MSSM, which we've ignored so far. Okay, and soon it's surprising to me, but because the way this course is structured, that we aren't actually doing any calculations and writing down, doing anything that would amount to detailed diagram calculations. It's actually going very fast, somewhat superficial but fast. And so we'll be able to do the Higgs sector, and then we'll actually get started talking about what constraints on the MSSM come from some high-scale physics, including assumption of supergravity and so on. And then, having covered that at some level, we'll conclude by the end of this month or early next month. And then we'll go on next semester for those who are interested to have some guest lectures and study. Okay, so let's define a 6 vector called F. This thing makes it a 6 vector, that thing makes it a fermion. I hope you can remember all these things. And it consists of three vectors, FIL and FIR. And what I've claimed is that this whole thing will mix. Any mixing within this is intergenerational mixing. Okay, for example, between selectrons, muons, and staus, or between up squarks, charged squarks, and top squarks, something like that. The same within this block of 3 objects will be a mixing between the right squarks or selectrons, and then mixing between this and this will be left-right mixing for fermions. Okay. So specifically, these 6 vectors are EIL, EIR, 6 selectrons, then an odd one, the neutrino, which certainly exists on this side but doesn't exist on this side, so just 0. So just treat it as a 6 vector, which happens to be 0 in 0 of its components. Then the up squarks and the down squarks. So that's what these are the only 4 possible choices for that 6 vector. These are the 4 6 vectors. And emphasize that while mixing takes place among all components of one of these, it doesn't take place across these. So for each of these you can study mixing separately. Okay. So what would be the generic mass matrix? We call it MF tilde square, and this can be thought of as a matrix which has a left component. So this is a 6 by 6 matrix which I am writing as 3 by 3 blocks, and it acts on this, which is divided into 3 plus 3 elements. So I think the notation is pretty obvious. So that's the matrix. And we do need to write out this matrix so that we can study it a little bit more in detail. Now I'm a little unsure whether I want to write it for all the electrons. Why don't I write it for the electron, for the selectrons, and then we leave all the others to sort of imagination. I did this last time in some other notation, but it's basically the same thing. It just consists of going through the MSSF plus soft terms, giving the Higgses their waves, and then picking up all the terms which contribute to these masses. Okay. So it's very easy. And then one more step is to replace some of the parameters by physical masses using well-known relations. So for example, if you encounter some SU2 or SU3 coupling or SU2 coupling constants and U1 coupling constants, you can trade them for masses of Z's and W's in this way. This is the top left part. It's a little awkward to fit it all in one blackboard. The top right part is minus NT. I'll explain. Then what? This is the top left. And this is the top right.
This is a similar structure, this block.
Sorry?
So this is a similar structure to the last block.
Yeah. This block is this one, and this is this one. And I have to write two more. But there's just this one on the bottom left is just the transpose of this, so it's minus transpose. Remember that tan beta is the ratio of two Higgs waves. And finally on this, that's this block now, and then this block is very similar to that, but not exactly equal. And then plus a third term which is actually identical. Okay. So let's just, sorry for this mess, but I hope you can decipher it. Let's understand why it's like this. Well, some things come from soft breaking terms, some come from the superpotential I wrote. So these M's are soft breaking terms. So they enter here, for example, and here. And because this is the left block, this is the soft breaking term involving the left selectrons. And because this is the right term, this is the soft breaking term involving right selectrons. So that's easy to guess. Okay, this one is a 3 by 3 unit matrix. This term is the mass matrix for the leptons, not the selectrons, for the fermions themselves. And it so happens that in the approximation, when neutrinos are massless, when right-handed neutrinos are absent, and neutrinos are massless, then this matrix is diagonal across the 3 generations. But for quarks, the analog matrix will not be diagonal, so this will not be diagonal. Okay. And the same matrix occurs here in the off-diagonal case. A is a parameter I just wrote down before, which occurs in the soft SUSY breaking cubic terms. And mu is the H1.H2 coupling you saw, and tan beta I have already mentioned. So I think everything is clear. There's really nothing new in the case of quarks, except that some of these numbers change. For example, this actually turns out to be the isospin. So this is plus a half here and 0 here, because this is the left side where the electron has isospin. This is actually minus half is the isospin component of the electron, and here there isn't any analog because this is the right-handed electron which doesn't have isospin. For quarks, this will again be plus or minus a half, and here actually you'll find the charge which is plus 2/3 or minus a third. That's the only change. Okay. So comments. So one is soft SUSY masses for both left and right fermions appear. Second comment is that the Higgsino mass parameter, remember that the Higgses got their mass from this coupling mu H1.H2 because there wasn't any coupling we could write which would give a mass directly like H1 squared or H2 squared because of holomorphy of the superpotential and the charge assignments to H1 and H2. So the Higgsino mass parameter is really mu, call it the mass parameter. I mean, it's the Higgs mass parameter, there's also the Higgsino mass parameter. Maybe I should call it Higgs mass parameter. Mu, and it's complex, that's important, also appears here. But it appears only in the off-diagonal terms, the left-right mixing terms. Okay. Comment 3, which if you look at your notes from last time, you will see that I have done it, is that D-term contributions to the above are diagonal in generation space. Okay, so these are D-term contributions, this and this, and the ones come from the fact that the D-term contributions are diagonal in generation space. Okay, and the fourth comment is that LR mixing, that is the off-diagonal terms here and here, are proportional to fermion masses, not fermion but fermion masses. And that proportion, by that proportionality, I mean the occurrence of ME dagger here and ME here. These are the fermion masses. They happen to be diagonal, so I could have written this as ME times 1, but then this need not be diagonal. But in the case of up and down quarks, even these M's here and here are not diagonal. The important point being that the off-diagonal ones are entirely proportional to M, while the diagonal ones have these M squares appearing, but they are not the only terms. It also follows because of this proportionality and the fact that the fermions in the standard model already, and therefore also in the MSSM, are heaviest in the third generation. That's of course how we rank the generations. The first generation is the lightest, third is the heaviest. So these off-diagonal terms are largest for the third generation. So these are some comments that apply to this matrix, and you can apply the same, precisely same comments to the quark mass matrices. I mean quark mass matrices. Okay. Now you can diagonalize as we always try to do, we'd like to diagonalize these mass matrices. And for the purpose, we use bi-unitary transformations. And the matrix which does this is called W. It's very easy to run out of notation in this subject. If F tilde M are the mass eigenstate fermions, then they are the 6-component object, each of which has a definite mass. S is a label which goes from 1 to 6, and these should be the summation over some. These should be a matrix rotation of the matrix W S T, summation T going from 1 to 6. This matrix is called W F tilde, and the way it's supposed to act, this is actually star for some reason, and actually I think this is TS. So it's W dagger ST which I'm using, and times the original basis. Okay, then in that case these are the mass eigenstates. Good.
The S is the 6 vector.
Yeah, S goes from, sorry, excuse me. So, yeah, that's correct. Yeah, S is the 6 vector index, so is T. So these are the 6 components of the usual fermions, and those are the 6 components of the mass eigenstate fermions, which will no longer necessarily have a left or right label or a generation label, because precisely because they're mixed up. Now, there are some special cases, and let me just show you what the special cases look like. So one of the special cases is no left-right mixing. In that case, this W is equal to 0 there, because it doesn't need to mix all the 6 components, but just needs to diagonalize the top 3 and bottom 3 separately, and so it takes the form U F tilde left and U F tilde right, where these are separately unitary matrices.
Right.
And they're 3 by 3. The second case is that there is no flavor mixing, but there is LR mixing. And in this case, what happens is that out of the 6 components of F tilde that we described, it's really F tilde 1, which is the first generation left squark, can mix with F tilde 4, which is the same first generation but right squark. Okay, 2 can mix with 5, 3 can mix with 6, so it doesn't take a huge degree of mathematics to realize that in that case the mixing matrix looks like cos theta of the first generation, cos theta second generation, cos theta third generation, cos theta. Well, let me define this more simply. I think it's pretty self-explanatory, but anyway. C1, C2, C3, C1, C2, C3, then all zeros. And in these blocks, minus S1, minus S2, minus S3. In this block, plus the same thing. Where C1 and S1 are cosine sine from one angle, which is the angle that mixes the left and right first generation fermions, and C2, S2 and C3, S3 are the cosine and sine for the other generations. And you see that if you look at this matrix properly, it's just doing a mixing C1 minus S1, S1, C1 on the 1 and 4 components, and then the same on 2 and 5 and 3 and 6. So this is the possible limit of the mixing matrix. Yes.
So these special cases, are they attained for some value?
Yeah. Well, that's correct. They are attained for some value of all the parameters, not only soft breaking parameters. And they're always approximate, but we've more or less seen. For example, we saw that the LR mixing is suppressed in the limit when the fermion masses are very small. So, for example, it might be possible to neglect it within. So, one thing that's often done is to consider the three generations of particles and sparticles in a slightly different way, where the first two generations mix, but the third one doesn't mix with the first two. That's often done. In that case, you'll find that within the first two generations, you can put these things to zero within some range of parameters. So, there are many different and interesting limits, and we will be talking on them. In fact, I am immediately going to talk about this third generation. Okay, so these were special cases. So here's the third special case, in fact, third generation. So this is a case in which we assume that flavor mixing is small, namely the third generation doesn't mix with generations 1 and 2 very much. But LR mix, left-right mixing is large. In fact, clearly it's largest because I pointed out that the off-diagonal elements in the mass matrix depend on the fermion mass, and that's the largest in the third generation. Even more than that, it's largest for the top quark by a huge factor, nearly 40 or 50 or something. So it really will be with the top quark, it will be most interesting. Okay. So this means because of the large masses, the large fermion masses, we can treat the tau, this is what the stop as having their own 2 by 2 mixing matrices decoupled from everything else, and the only thing they do is to mix the left and right solids. So let's see an example. The tau tilde, which is this tau, will have a mass matrix. Actually, I don't see any point writing it again. It's just the same as the thing I wrote earlier, but instead of being 4 blocks which are 3 by 3, there are 4 blocks which are 1 by 1. Just the intergenerational index I is suppressed. So, for example, here you have M L3 tilde squared minus sine squared. Usual stuff, plus M tau squared. And all we've done is drop that index I and just put the contribution appropriate to the third generation in every place. So that's another special case. Okay. Now here's a consequence of this fact. Let's ask the question, which is the lightest fermion? This is obviously a question of direct experimental relevance, because it's the one we expect to find most easily. And the point is that given if we are allowed to think of these as 2 by 2 matrices, which is true in the third generation, then it's pretty easy to see that what we need to have a lightest fermion is of course a small eigenvalue. So is there anything which can make this matrix develop an eigenvalue that's very small compared with what you might naturally expect just from these diagonal terms? And the answer is the off-diagonal terms should be able to compensate so that the determinant is much smaller than you have expected. Okay, so in third generation you can actually argue that it's in the third generation that you're likely to find, or it's possible to find the lightest fermion. Off-diagonal terms being largest. It could happen at don't say it does happen, but it could. That delta square is smallest. Or, well, I don't know, there must be a better way to think of it, but m square develops a small eigenvalue. And in fact, because the top quark is by far the heaviest, being about 175 GeV as compared with all the others which are about 4 GeV or less, that's the most likely place where these off-diagonal components will be so large that they'll be able to bring down the lowest eigenvalue of this from the naive value. By the way, notice that this is a sum, at least it used to be all positive. Maybe I'm writing here in the electronic sector it's not, but in quarks I think it's all positive terms. This is not nice. No, it's only for the up quark that I was finding all positive terms. Anyway, I'm not doing this analysis very precisely now, but it's likely we'll come back to it. So, off-diagonal terms being largest. So this implies that the lighter, so every fermion will have a lighter and a heavier particle, being the eigenstates developed from the left and right, if we just ignore intergenerational mixing. So there's a lighter of the two stops, and this can be the lightest fermion. That doesn't automatically mean it's the lightest supersymmetric particle, because there are K-genos and there are other particles. But among this fermion sector, this has a good chance to be the lightest one. Okay. So it's a rather nice paradoxical situation that in fermions the generations are ranked by having lighter fermions first and the heavier ones last. But precisely because of that and this possibility of mixing, it could happen that the fermions are ordered in a different way. That is, the fermion partners of the up and down may be heavier than the fermion partners of the top and bottom. Okay. This is not a watertight conclusion yet, because remember that the masses, the large masses of fermions which occur here, multiply some soft parameter like A, which is up to us in principle, and maybe some model sets it to 0, as well as it multiplies mu tan beta, so it depends on those parameters also. Still, it's worth remarking, and we'll come back to that in another 5 minutes because I'll have something a little more specific to say. So, are things clear up to now? Any questions, comments? Okay.
Is there some limit at which you get zero mass for the? Could you get a massless?
Could you get an arbitrarily small mass for the stuff? I don't think so. But I'll admit I haven't played around. So I think the way to find out would be to take this 2x2 matrix, do it for the stop, left and right stop. And MZ we know, theta W we know, beta and mu we don't know, but we could propose something. And the most sensitive, the thing on which it's probably a sensitive function is this A parameter, which parameterizes the qubit couplings in the soft breaking terms. And up to now, we haven't said a word about what it is. It could be 0 or it could be infinity. So I suppose that would matter a lot. So I think in order to know more, one has what I understand from whatever I've been reading is that this is a kind of stage where the model has the maximum number of free parameters and you're groping to find some universal property or to find some assumption which simplifies the model. And we'll see now in a moment that right now this model runs into an experimental problem which is called the flavor problem. Potentially runs into this problem. And I'll explain this in a moment. And then we'll see that if we want to get around the flavor problem, then we have to make some assumption, and there are 3 classes of assumptions you can make on these parameters to solve the flavor problem. Okay. Then once we've solved the flavor problem, we could come back to your question and say, okay, within this solution to the flavor problem, when this set of parameters are constrained in such a way, is it possible to make the stop very line? But we can't arbitrarily ask that because there are other constraints. So I think the literature sort of always tries to address the most potentially severe constraints first, which is obviously the right thing to do. Okay, so the problem here involves the absence, as detected by experiment, of flavor changing neutral currents. And a very simple example of that is the muon decaying to just an electron and a photon. It just doesn't happen, but it wouldn't kill us if it did. I mean, it might kill us, but it wouldn't be inconsistent with any. It wouldn't be inconsistent with any great principle of physics. But for some reason, muon numbers separately conserved from electron numbers.
Neutral means you charge, you uncharge, electromagnetic.
Yes. Okay. Now, there are many consequences of this absence, but okay. So, the point I'm trying to make is that this generic mixing I've been writing here could generate processes which would do exactly this, which we don't want. Okay, so this is one example of the flavor problem. More generally, fermion mixing should not. See, fermion mixing is a fact at tree level. We have no prejudice about what the masses of these fermions are, since we never found any fermions yet. So we can live with anything. But they will occur, these mixed fermions will occur in loops, and they will cause conventional particles, including ordinary quarks, to mix, and these mixings will be the flavor problem if the mixings are larger than the experiment allows. So fermion mixing should not lead to radiatively to unacceptable fermion mixing. So what's an example where this could happen? Well, there's a very famous example of fermion mixing. I'm not sure, but it's probably the first example ever known. That was in the K0 bar system. So let me remind you what we know about the K0 bar system already, and then I'll try to show you that these fermions could ruin things for the K0 bar system, which is well measured experimentally and well explained by the standard model. So the last thing we need is for it to be messed up. So K0 is a ds bar, the neutral meson, and the K0 bar is obviously its CBT conjugate, so it's a d bar s. I think this is right, this is what I got out of a book, but I'll confess that I don't know why the K0 has the strange bar. I would have thought it would have done this convention. So no past, you know?
Strange is -1.
Because the strange quark has strangeness -1, so the K0 is defined to have strangeness +1. Thank you so much. Very good. Okay, so what makes them mix in the standard model? The following diagram. Following pair of diagrams really. So here is S and D bar. So this thing is the K0 bar. Here I want to get out D and S bar. So this should be the K0. How do I achieve this? I achieve this for the following reason. The D quark, of course, couples to the U quark. That's just what the standard model SU2 does by the emission of a W minus. So this vertex is well known. But because of mixing between first and second generations, there is a Kabigo angle, and the sign of that Kabigo angle governs the fact that a U quark can go instead into an S quark. The U quark in the first generation can decay into it can go through this vertex into an S quark, which is in the second generation. By also giving off a W minus, this quantum number is unchanged. It's just that naively, without mixing, this would be of some strength 1 in some units and this would be strength 0. But after mixing, this is cos beta and this is cos theta c and this is sin theta c, where theta c is the Kabigo angle. And likewise on the other side. So here's a diagram. There's also another diagram, but I needn't write it down. Anyway, the key point is that this mixing implies that K naught bar are not the mass eigenstates. Which instead are two neutral self-conjugate particles, which are called K long and K short, which are linear combinations of K naught and K naught bar. And they have different lifetimes because they decay differently. And the important thing is that they have different masses as a result. Generically, mixing always leads to different masses because obviously if there weren't different masses, then it would undo the mixing. And the experimental result is that the mass of K long minus the mass of K short is 3.5 into 10 to the minus 6 eV. Okay, and that's basically accounted for by these diagrams in the standard model. So if the MSSM with soft breaking is going to make the mixing much worse, then we could be in lots of trouble. So what does supersymmetry do? It adds a new diagram. And in this new diagram, so on this side we again have the K naught bar, on this side we again have the K naught. And so these are the same, the external legs. Okay. But this time we get any one of the squarks going here. So I denote this by a D tilde IL. Basically what I'll do in this diagram is to assume that everybody is left-handed. So we'll just look at this diagram in a situation where there is no left-right mixing, which remember was not such a bad assumption for the first two generations, and K naught lived in the first two generations. But D tilde IL are respectively the down squark, the strange squark, and the top and the bottom squark, which we'll neglect. So this I can be just taken to run over 1 and 2. So what I'm saying is that the strange squark can go into a strange squark or a down squark. Okay, and what it can do this via exchange of a gaugino, which will be a vino, which is denoted this way. So here are gauginos, and then this thing is completed again by having a down squark going the other way. So here's the diagram. Okay. Now, there's a brief calculation given in DGR, which I'm not going to spell out, but I'll just tell you the answer. So this is proportional to sorry, did I say that right? These are not vinos. Did I say they're vinos? These should be gluinos, I would think. The gluinos, this process is a strong interaction process.
If you want the generation mixing, it should be something weak.
Yeah, I got confused suddenly. Maybe I said it right to start with. The question is what gaugino takes a quark. So let's assume, for example, yeah, these are neutral.
SL and D tilde IL have the same quantum.
They have the same quantum numbers, that's correct. They have the same charges in particular.
So it can't be W.
So it certainly can't be W, can't be Venus. but gosh, momentary confusion, which I'm sure will look very embarrassing on the camera once it's solved. So what is it, a Z, Xeno, or is it a Gluino?
And it's just because everything in the strong interaction is diagonal in flavor.
That's correct.
From the initial transformations of both.
That's correct, but but that's fine because one of these is diagonal in flavor, right? SL will go into S tilde IL because S tilde L, which is D tilde 2. D tilde 2 is the strange squawk. So that one is diagonal for sure.
And then when it goes into
On the other side. That's correct. Of course, in order to mediate this process, it's clear that one of these, so two of these can be flavor preserving and two will be flavor changing. That's correct. I'm just trying to remember what the vertex is which does this, because that would determine the answer. Because in my notes, the answer has a GS. GS cannot be G string much as we would like it to be, but I thought it was G strong because this is important actually. Okay. Anyway, it's obviously some G to the 4th power, and this is something they've called GS. But I assume this is anyway, whatever it is, it's not in our control. But it would be nice to remember what it is. Okay, anyway, let me go on and write this thing down and we'll double check this later. So I'll write it and then I'll explain the notation. So here, unfortunately, the notation becomes a little. I think this is not a very good notation by these people. I think that, well, yeah, I want to write it this way. 1 is the first generation, 2 is the second generation. So we are trying to find an amplitude which mixes the first and second generations. So they've written it as UTIUIS, but it's not very clear then that T and S are quarks rather than indices. So I'm writing it as U1IUI2, and this is dagger. And these are the components of those unitary matrices which diagonalize these fermions. And then there's a mass difference here, delta M D tilde IL squared mod, and then we're supposed to square this. So the claim is that the rate of this process is proportional to this, where M tilde is the larger of average fermion mass. Remember, for this purpose we can be in 2 generations, and kg no mass. So in particular, we can manage to make the average fermion mass very heavy, in which case the M tilde will be that. And so what we do is we take the 3 fermions, because we are not doing left-right mixing, so there are 3 left fermions. We add them all up, we add up their mass squares and take an average that goes there. And then we take the deviation of their masses from the average and that goes here. So the delta M's are the deviations of the 3 fermion masses from the average value. And U's are the matrices that diagonalize the fermion mass. So everything in this expression except for G to the 4th is clear. And now we have to ask what we should do to make this small. How to suppress this convolution. One more comment I want to make, and I apologize because I got a bit late working this thing out. I couldn't resolve a conflict between 2 sources in the literature. This U should actually be somehow not the unitary matrix that diagonalizes the fermions, but the ratio of that to the one which diagonalizes the fermions. So this is really like U D for the down-drive fermions times inverse times U D tilde. In other words, if the mixing between these fermions is parallel to that between the fermions, if it's identical, then these U's will be 1. Okay. That's what I think it should be, and that's also logical because these vertices are each proportional to a mixing for the fermion as well as a mixing for the sperm. Okay, so the way to make this small, there are three, and these are three scenarios. So now we start getting constraints on all our various parameters. The first one goes by the name of inverted hierarchy of fermion masses. There's another use of inverted hierarchy in the literature for neutrinos, for neutrino masses. That's a different subject. And this is based on a very beautiful fact, which is make the first and second generation fermions very heavy, around 10 TeV. Probably I should have said first that the three ways of making this, suppressing this, involve suppressing either this factor, using this factor to suppress it, or using this factor to suppress it, or using this factor to suppress it, because that one is not under our control anyway. Okay, so this, and of course, as it's been clearly said in the books, you can also use combinations. You can use all the possible ways of suppressing it a little bit, but let's consider the extreme cases where you suppress it entirely using one or other of these factors. So method 1 is to make the first and second generation fermions very heavy, about 10 TeV. It turns out if you want to rely only on making this large, then it has to be 10 TeV. That's the number which makes this small enough to not contradict experiment. The problem is, this is the average of all the fermion masses. So why am I harping on the fact that only the first and second generation fermions have to be heavy? Why couldn't I have just said that all are 10 TeV? And the answer is, we cannot make the third generation that heavy. The third generation fermions greater than even a TeV. People quote more like half a TeV without spoiling naturalness. Now, in turn, you may ask me why. Why is it that the third generation fermions being too heavy would spoil naturalness, but the first and second would not? The reason is that what spoils naturalness also involves the Yukawa couplings of these fermions, and the Yukawa couplings of the third generation fermions are the largest. Okay, so this is the interesting thing, that the Yukawa couplings of third generation fermions being largest, that we had to do in the standard model to make the third generation fermions heaviest. Okay, but those Yukawa couplings also participate in the role of fermions to cancel quadratic divergences and make supersymmetry, solve the hierarchy problem. Okay, so those Yukawa couplings in the third generation being large bounds the masses of the fermions in that generation. And so there's a kind of, again, an inverse effect. We saw it a few minutes ago, and now we're seeing it more sharply, that the third generation fermions would like to be light, or we would like them to be light, because otherwise solving the hierarchy problem becomes hard. And so their contribution cannot be the one which makes this go above 10 TeV. On the other hand, the first two generations fermions couple through their Yukawa coupling, which is much smaller, and so they have the freedom to be as heavy as 10 TeV. Okay? And now it's pretty clear why we have an inverting hierarchy. In the first and second generations, the fermions are lighter than the third generation, but these fermions are heavy. Okay, so that's the solution. I think I'm going to end a bit early today. Anything more to say now? Okay, so I'll just briefly mention the other two solutions, and then I'll end. That's pretty much at the level of what we want to discuss with fermion masses. So I think I'll stop with that and go on to other things from next time. So solution 2, oh dear, I erased the formula that we needed anyway. Solution 2 is called alignment. Okay, so here what you do is make the fermion mixing matrix proportional to the fermion mixing matrix. So I promise that next time I'll briefly tell you why in that form, I'll tell you exactly how that formula is written, which I wrote today, and try to show you that the unitary matrix there is really U of fermion mixing times U dagger of fermion mixing. So it's a matrix that becomes 1 if alignment is true. But if alignment is true, then obviously any sum involving U1I, UI2 will obviously go to 0, because U then becomes, doesn't matter if it's a dagger or something, it just becomes diagonal. So there's no chance that there's no chance that both of these can simultaneously contribute. For this to be non-zero, of course, they need to be non-diagonal, because this becomes diagonal. So that puts the unwanted K0 bar mixing to 0 for an independent reason from this inverted hierarchy. Okay, of course, neither with inverted hierarchy nor with this we have any reason why we are doing this. We are just trying to do this as a phenomenological fact. But obviously, then we would like to see what models favor, what high-scale models favor the achievement of these properties, either of inverted hierarchy or of alignment, in which somehow despite supersymmetry being broken and broken by soft terms, but which come from some spontaneous breaking, it's possible that somehow the generational mixing remains valid, remains the same for the fermions and less particles. Yeah.
But would the inverted hierarchy also work with BP?
Will it also work if?
With BP.
So what do you mean, will it work with
B0, B0, B0?
Yeah. Or will it solve the problem of B0, B0 bar mixing? Yeah, I don't know that. Actually, there is some mention of what possible mixings are dangerous, but I can check up and let you know. But I assume, yeah, I guess one would have to see the diagram, but I assume it's
your point is that it's third.
That involves the third generation. So the question is whether, yeah, indeed, because you make the third generation fermions light, whether that would be a problem. But of course, the third has to mix with the first and second. So it seems that, I mean, the third obviously has to mix with the first or second. So somewhere in the formula, one would expect that these heavy masses come in a denominator. And if the mass is really, in fact, if we take the formula we wrote seriously across 3 generations, instead of K0 bar, imagine an abstract meson that involves 3 generations and mixes arbitrarily. I bet that the formula is similar because we didn't really make any great assumption except limiting it to 2 generations. Except for one thing, which is that the CKM phase can always slip in, but I don't know, somehow being a phase you'd expect it doesn't be particular. Good. And solution 3 to the flavor mixing problem is degeneracy. This is the easiest one to guess. Just assume that the fermions are all degenerate. They don't have a mass difference. So obviously that's a way to get rid of any mixing problem, because once things are degenerate, then there's no mixing, because mixing can always be undone by change of basis. Okay? So comment would be that in principle combinations of what were they called? Inverted alignment and degeneracy could be used so again, even at our very, what I think of at least as a very crude level of phenomenology that we are talking here in this course up to now, once one understands this point, then in a few years, if you learn that there's some indication of degeneracy or some indication of alignment, then things start to focus on one scenario of absorption breaking terms. So you can see that the road from these observations to experiment is not that far. Okay, good. With that, I have run out of anything to say more today. And next time, after maybe tidying up a few little things, I will start on the Higgs sector of. Okay, I just mentioned perhaps that Shiraz had a suggestion that at some point, but I think next semester might make sense, we look at this LHC Olympics and try to understand how people reconstruct a theory based on data, or at least, as Shiraz put it, at least we learn first how to construct data based on the theory, and then hopefully we learn the inverse problem. I mean, this is certainly these practice exercises will certainly help us. But it's also true that we need more. We need to, as string theorists, particularly, we need to focus more on the many high-scale scenarios and things that Sandeep is going to tell us next semester. So, that if this group goes on for a while, we can do all these things. Okay, thanks. Don't Rahul, unless you know how to stop it.
Just stop sign.
Stop sign. Yeah, but don't hit the one which is stop and erase the tape. So maybe just why don't we just call a day? I think we'll do it.
Okay.
Let's see if you can stop it.
I'll just press record again.
No. Don't do that. Are you crazy? Okay, start, stop. This one, no?
That will put a problem.